Hey, Math 7195. Here we are in unit number 9, video 1. In the previous videos, we were comparing two population means and two population proportions. Today, we're going to do two population variances. So basically, the standard deviation of one group versus the standard deviation of another group. In order to do that, we'll have to introduce a new distribution called the F distribution, and the test is called an F test. Let's get to it. So, to compare two variances, I'll need to give you a new test statistic and some new assumptions. Once again, we're comparing two independent populations, and in this case, they have to be normally distributed for this test to work. This is an important one for this test. This is one of those places where statistics can get abused. If you don't know that your populations are normally distributed, this test can fail. The F test for comparing two variances relies on an F distribution. Basically, it's looking at ratios. So we're going to be looking at the ratio of the standard deviation of one group, or variance, because we're squaring it, the variance of one group to the variance of another group. And we'll just look at the ratio of their variances. That can be modeled by this distribution here on the right called the F distribution. Again, it has it's one of those distributions that has quite differing shapes depending on various parameters, and in this case it's degrees of freedom, like the T distribution. Its shape depends on the degrees of freedom of the numerator and the degrees of freedom of the denominator. That's what this dfn and dfd, n for numerator, d for denominator. It's just n minus 1 for each of them. And then the shape of the distribution depends on those degrees of freedom. And the mean can also be defined in terms of the degrees of freedom. So you can find the mean of these distributions using this formula, and it can all be done with the degrees of freedom of the denominator. When we're choosing which group to call group 1 and which one to call group 2, the way we will choose that will be to call group 1 the one that has the larger variance. So that will help keep this ratio greater than 1. And as we see this distribution, most of the values are greater than 1. So you can see this distribution is unique from previous ones that we've had in that it isn't symmetric. So if I give you the right-tailed table, it doesn't necessarily help you find the area in the left tail. There is a way to do it using a bit of a transformation here. You can get the left-tailed value from the right by doing, it's just the inverse of it. So 1 over the area in the F value in the right side is equal to the area in the left. It's not too big of an issue for us because we can always use Excel to get our F values. We don't have to rely on the tables because the tables are it's hard to come up with tables for this because there are so many permutations. The F distribution depends on two different parameters. So the number of F tables that you need gets to be quite large in a hurry. I have an example of one here. Here's the F distribution only corresponding to an area of 0.05 in the right tail. And then across the top axis, I have the degrees of freedom of the numerator, and down the vertical axis, I have the degrees of freedom of the denominator. and then these are our critical values in the table. So say we had a numerator of 6 and a denominator of 10, our critical value would be 3.22. It would look something like this, and 3.22 would be here, and the area to the right of it would be 0.05. It's really hard to use this to calculate p-values because basically we need a different table for each probability. In the t-table, we have each column of the table is essentially a different probability, but for the F distribution, we'd have to have a separate table itself for each probability. I believe in your formula packet, you have the F distribution table for 0.05 and for 0.01. But we can always use Excel to get these values if we need them, which is probably easier because then we have more options and we can be more precise anyway. Here's a little example. We're comparing how much weight a can handle. You put a weight on top of the can and you see what load it can handle before it crushes. We can design the can using different thicknesses of aluminum. So suppose we use 0.0109 inch thick aluminum versus 0.0111 inch aluminum. So these are the thicker aluminum cans versus the thinner aluminum cans. Comparing the means wouldn't be very interesting. I mean, it seems pretty obvious that the thicker the aluminum, the more weight they can handle. So I'm not surprised that the mean load of these thicker cans is 281.8 pounds, whereas the thinner ones, it's lower at 267.1. I probably don't even need a hypothesis test to check that the mean of thicker cans would be higher than the mean of thinner. But maybe there would be more variation or less variation depending on thickness. So maybe we'd like to compare their variance rather than their means. I've listed the standard deviation here just because we're, more familiar with it, but the test is technically a test of variance. Let's do the test. The claim is that the thicker cans have a greater variance than the thinner ones. And we decided that this meant thicker than these. When you're deciding how to set these up, remember we have to decide which group is group 1 and which one is group 2. And in order to do that, it's the one that has the larger variance. So it's the one with the larger standard deviation. So in this case, group 1 is 27.8 squared is larger than 22.1 squared. So be careful there. Don't just work left to right. Whichever one has the larger variance, that's the one you call group 1. And in this case, group 1 is the thicker can versus the thinner can. Let's start writing it out. Formal steps. Step 1, the claim is that the thicker cans, which is group 1, have a greater variance than the thinner one. So that'll be sigma 1 squared is greater than sigma 2 squared. That's their claim. These units were in pounds, so our variances would be in pounds squared. Step 2, set up your hypotheses. Your null and alternative hypothesis. This is going to be the alternative hypothesis because it doesn't have an equal sign. So we'll say sigma 1 squared greater than sigma 2 squared is the alternate hypothesis. and then the null is that they are less than or equal. Then we can move on to step number 3 and set our alpha. They told us to use 0.05. Step 4, check your assumptions. In this case, we need normal distributions, and this data had to be randomly sampled. When we meet these conditions, then we can use the F distribution. Now we can move on to our test statistic. This is a nice one, easy to calculate. It's just S1 squared over S2 squared. So our S1 was the 27.8, and our S2 was 22.1. Remembering to square them both, you get 1.5824. Step 6, we have the two methods. Take your pick. You can be a p-value or a traditional. Suppose we do the p-value method. Is this a left or right-tailed test or two-tailed? Well, looking at HA, it's pointing the way. This is a right-tailed test, which is nice because that's the way our table is. I'll just draw some sort of sketch for an F distribution here. We want the area to the right of 1.58. We want this area. In order to get it, now that is the p-value. It's the area. We're going to need to know the degrees of freedom. The degrees of freedom of the numerator are n minus 1. There were 11 values in the numerator and 26 values in the denominator. So it's 11 minus 1 is 10. And the degrees of freedom of the denominator were 26 minus 1, which is 25. So we go to back to our F table, and we're looking for degrees of freedom of 10 for the numerator, and I believe it was 25 for the denominator. And this number obviously isn't going to match our 1.5. Basically, we would have to look at this table for 10 and 25, and then look at another table for 10 and 25, and look at another table for 10 and 25, until we find our test statistic in the table. And in this case, we didn't find it. We know that if you're at 2.24, the area to the right of that number is 0.05. So wouldn't it be safe for us to say then that if we're at 1. What was our test statistic? 5.8? It's going to be more, right? I don't know what this area is, but it has to be bigger than that one. So my p-value is going to be greater than 0.05, even though I wasn't able to find it in my table. And that's enough in order for us to make this decision here. So even though I couldn't find it in the table, I know that it's greater than 0.05. And that is, important because that's what our significance is for this test. So I don't know what's going on here. Trying to put more space in here. There. We can make our step 7 here. Step 7. Our p-value is greater than 0.05, which is alpha. And when p-value is greater than alpha, we fail to reject. And then step 8 is our conclusion. Back to the setup here. If we don't reject the null hypothesis, in this case, then we're not supporting the claim. There isn't enough sample data to support this claim. We'll say that. There is insufficient sample evidence. At alpha equals 0.05 to support the claim that the thicker cans have greater variance than the thinner cans when it comes to testing them for axial load. I know that didn't feel very satisfying when we did the p-value so crudely. If we needed that p-value more precisely, we could of course use Excel there. It's a probability. The function is f_dist, and because we want it to the right here, there's a right function, and then we just put in 1.58, and then we put in our degrees of freedom of the numerator and the denominator, and we tell it that I don't think you have to put cumulative when you're going to the right, and you get your result. The answer is actually quite high. It's 16.9%, so 0.1696778. I'll do it in Excel. I thought maybe we should squeeze in the traditional method. It might be a little more satisfying with the table. So we'll do a traditional right-tailed. In that case, we're looking for a critical value, f sub alpha, where the area to the right here is alpha, and our degrees of freedom are 10 and 25. And we already looked this number up. This is the number we found it in our F table. It was the only value in there for 0.05 at numerator 10, denominator 25. It was the 2.24. So that's our critical value. So anything to the right of 2.24 is in the rejection region, but our test statistic was 1.58. So it was, say, there. So we are going to fail to reject because it's not in the rejection region. So using the table, using the traditional method isn't bad. You get a pretty nice, you know, a more concrete answer than, this is a little wishy-washy over here, unless you have Excel to get the function. In fact, if you wanted to get this number without the table, say you didn't have 0.05 and you were using alpha as 0.03, well, then you could use f.inv, and that will give you this value. But remember, the main function without the dot right is well, they're always to the left in Excel. So you'd have to put in 0.95 and then your degrees of freedom of 10 and 25. You can see how the order of these things matters. You have to be careful about which you call group 1 and which you call group 2 so that you get your degrees of freedom correct, so that you're in the right table. I don't know if there's a f.inv .right. I think there is actually. Then you can just put in the 0.05. Let's check. I did this with Excel. I copied and pasted the question that we're doing. I actually took a picture of it, so I had to recreate the table. Excel, again, doesn't have a built-in f-test when you're given summary data like this. If we had the actual 26 values from group 2 and the actual 11 readings from group 1, then there is. Under data analysis, there's something called f-test 2-sample for variances, but it requires that you have the raw data. You have to have a range of values, and you can't. I tried it, but these are not the ranges of values. These are summary stats. But you can see it's similar to the inputs that we had for the 2-sample t-test for means. Again, you need the data. So if you don't have the data, then you have to do it old school like we just did, where we calculate f, and then we find our critical value if you're a traditional person. Oh, and there was a right. f.m.right to find the critical value, which is the value in our table. And here's the p-value where you can find the probability to the right as well. So now you have a template for this as well. I'll post this so you can do your f-tests on your own, update the tables, update the formulas, and away you go. I guess you have to change, you have to reset them up. It's at least a good starting point if you're going to ever type one of these up. So, yeah, that is an f-test. We use the f-distribution for other things as well. We'll see a little bit later. But for now, this is our first use of an f-test, or f-distribution. And it isn't too bad. A new table, a new test statistic, but it's a really easy one. So I think you'll have no trouble with this, especially after all the ones we've done so far. I think that's where I will cut this one off for today, and I will see you all next time.